Today, we are diving into a technology that is, well, pretty much invisible. But it's the powerhouse behind some of the most ambitious science projects you can imagine. We're talking about everything from peering deep inside the building blocks of the universe to completely revolutionizing medicine. This tech is quietly changing everything. So let's get right into it.
So what is this hidden powerhouse? What's the secret sauce that lets scientists see inside an atom or even try to figure out what happened moments after the Big Bang? Well, the answer is surprisingly elegant, and it all comes down to creating a perfect echo.
That's right, a perfectly engineered echo. But we're not talking about a sound echo, not at all. We're talking about an echo of electromagnetic energy, an echo so pure, so perfect, it can sustain itself with almost zero energy loss. Now, you might be asking, what does that even look like in the real world? Well, it looks kind of like this. Meet the star of our show, the superconducting radiofrequency cavity, or SRF cavity for short. The easiest way to think about it is like a bell. A really, really high-tech bell made of a very special metal. When you strike it with an electromagnetic pulse, it rings with energy. But here's the magic part. Because it's a superconductor, that ring just keeps going. It barely fades. It's an almost perfect energy storage device. And it's the beating heart of modern particle accelerators. But, in the world of fundamental physics, almost perfect just doesn't cut it. For decades, the big quest has been to make this ring of energy as absolutely flawless as possible. And why? Well, because every tiny little bit of energy that fades away is wasted power. And when you're running these massive, city-sized experiments, that wasted energy really, really adds up. The number one metric here is something called the quality factor, or Q0. A higher Q0 basically just means a more efficient cavity. You can think of it as the difference between a cheap tin bell that just goes thud and a perfectly cast bronze bell that rings and resonates for minutes on end. Scientists, they want that bronze bell, and they've figured out some truly amazing ways to get it. And the progress they've made has been absolutely staggering. By using some really clever techniques like infusing the metal with nitrogen, researchers have just dramatically boosted this Q factor. This chart here gives you a sense of just how huge that leap is. The energy loss in these new high Q cavities is just a tiny, tiny fraction of the old standard. What that means in the real world is that we can build way more powerful particle accelerators that use way less electricity. Now, for years and years, the go-to material for these cavities has been niobium. It's a fantastic superconductor for sure, but it has one massive catch. For it to work its magic, it has to be cooled down to 2 Kelvin. That's just 2 degrees above absolute zero. We're talking colder than deep space. And to get something that cold requires these huge, incredibly expensive liquid helium plants. But now, a revolution in material science is changing the entire game. And folks, this is where the story gets really interesting. Enter niobium-10. This stuff becomes a superconductor at a much warmer 18.3 Kelvin. Now, I know that's still unbelievably cold, but scientifically, this is a massive leap. It lets us operate these cavities at 4 Kelvin, which is a temperature we can reach with much simpler, cheaper coolers. Think of them like super high-tech refrigerators, instead of those giant liquid helium factories. This one change makes the whole technology so much more accessible. And this isn't just a cool idea on a whiteboard. Over at Jefferson Lab, scientists put it to the test. They built the first accelerator component using niobium tin, and wow, the results were incredible. The official report said they achieved orders of magnitude higher Q0. In plain English, that means it was wildly, unbelievably more efficient than niobium at that same temperature. This was the proof. The game had officially changed. This is directly enabling the next generation of massive scientific instruments, the kind that push the frontiers of everything we know about the universe. Okay, take the Muller experiment. Its goal is to measure a property of the electron with such insane precision that it could actually uncover entirely new forces of nature, stuff beyond the standard model. To do this, the particle beam has to be stable to within 5 parts per 100,000. That's like trying to hit a target the size of a pinhead from a mile away, over and over again. You can only get that kind of ridiculous precision with the rock-solid stability of these SRF cavities. But it's not just about being super precise. It's also about raw, unadulterated power. The next great particle accelerator being built in the US, the Electron-Ion Collider, or EIC, well, it's going to be an absolute beast of a machine.
The core systems for the EIC need to handle 10 megawatts of power. To put that into perspective for you, that's enough juice to power thousands of homes. And all of that energy gets focused down into a tiny little particle beam. It's the quiet, ultra-efficient performance of SRF cavities that even makes it possible to manage that kind of insane power.
All right, now this is where the story gets really, really exciting for all of us. Because of these advances, especially with niobium-tin and the new cooling methods, this incredible technology is finally breaking out of the giant national labs and into our daily lives. What we're seeing now is the development of compact SRF accelerators. These are smaller, self-contained, almost plug-and-play units that use those simpler, cheaper cryocoolers. They don't need a massive support infrastructure around them, which means they can be put in places like hospitals, factories, and universities. And the applications this unlocks are just incredible. We're talking about sterilizing food and medical devices more effectively, creating specialized medical isotopes for cancer treatment right there on site at a hospital. They can even be powerful enough to break down those toxic forever chemicals in our water supply. Seriously, this isn't science fiction anymore. It's what's becoming possible right now. So the really crucial point here is that this has sparked a whole new commercial ecosystem. It's not just government labs anymore. You've got private companies like Radiabeam and Euclid that are now designing and building these systems. There's even a startup, Subcritical Systems, that's looking to use this tech to help create a safer form of nuclear energy. The field is exploding. But hold on, because perhaps the most mind-bending application is still on the horizon. The very same expertise that's used to create those perfect superconducting films, well, it's now being aimed at one of the greatest technological challenges of our time, the insane energy consumption of AI. The goal here is nothing short of creating a completely new kind of computer chip using superconducting logic. Just try to wrap your head around this. Chips that are 100 times more energy efficient and can pack 1,000 times more computing power into the very same space. As AI models get bigger and bigger, their energy use is becoming a massive, massive problem. This technology, this could be the solution that makes the future of AI sustainable. So let's just recap. We go from a perfect echo in a metal box, to understanding the secrets of the universe, to creating life-saving medicines, all the way to powering the future of intelligence itself. The journey of the SRF cavity is just this perfect example of how investing in fundamental science can lead to transformations we could never, ever have imagined. It really makes you wonder, what on earth will we unlock next?